This is the presentation that I prepared for ACTM 2025 in Ateneo de Manila University. And I am recording this video in advance just to be sure that it will be delivered on time if I will be not able for some reason attend the conference. This is the lecture that is the 13th part of the series Understanding Geometric Pattern and its Geometry. So you have seen the 12 already. Some of them were presented during the ACTM conference, and some of them were presented in EGMT journal. So everything is in your hands, and you can always check back and see whatever you want. Also, each of these papers, of my papers, was published on a ResearchGate website, so you can always find it there, and you can always see what I did recently. So let me to start my talking. First, I wish to tell you one thing. Most of the people, so-called geometric pattern lovers, they know a bit about hexagonal, octagonal, or decagonal patterns. They have intuitive knowledge about them. They have also some mathematical knowledge. But when they see a thing like this, I mean the pattern on the left side, then automatically they are lost because most of them, they have never seen it. So even just looking at the petals in this rosette or corners in this star, they see this is 14. If they know the word tetradecagonal, then it is fine. Otherwise, they are a bit lost. A situation is even worse when they see a thing like this. The pattern that you have here on the right side, it is really nice pattern, and it is made also in tetradecagonal geometry, but I'm sure not many people will tell you that this is this case. So first, let's try to say what we mean by tetradecagonal, octagonal, decagonal geometry and patterns in this geometry. So let's talk about polygons in geometric pattern design, but specific polygons. So on the left side, you have regular decagon and polygons that you can create on the regular decagon. It is quite easy. For example, when you have this trapezium, you just see a line like this, a line like this, a line like this. So this trapezium, it is just built between these four corners. That is perfectly fine. Each other shape will be built in similar way. So we have a long triangle, I call it long triangle. We have kite. A kite, this is really long triangles. Then we have rhombus like this, nice rhombus. We have also a rhombus like this one, and you can just make it, okay, just draw it this way, okay. And this rhombus, it is the rhombus that belongs to the decagonal geometry, so I prefer to make it like this. And also we may have a hexagon. It means a shape with 6 edges, and if you just count it here, you see that here we have really 2 lengths of edges. One like this, the long one, and short edges like this. If you compare these 2 edges, if we measure their ratio, then look what is happening. We are getting ratio between this one and this one, 1.61803. So this is the golden ratio. So we can just say this is golden ratio. In fact, the story is a bit more complicated. In decagonal geometry, we have golden ratio, but we have also another ratio that is associated with decagonal geometry, and not many people know about this, and not many people know its properties. But this is not the topic that we should discuss outside of this class. I wish to concentrate on tetradecagonal patterns and tetradecagonal geometry. Here I wrote something that is quite important. Each polygon has at least one symmetry line. So what is the truth? Most of the geometric patterns, when you build them on polygons, we are using symmetric polygons. Sometimes we have one symmetry line like here, sometimes we have one symmetry line like here, but here for the rhombus we have 2 symmetry lines. For the hexagon we have also 2 symmetry lines. For a regular decagon we have more symmetry lines at all. Now let's move to this right side. On the right side, what we have here a regular octagon. That's the another one. And we have polygons that were constructed on a regular octagon. So, for example, if I just draw a line like this, let's make it thin. And if I draw another line like this, so if I just have a circle like this, and a circle like this, okay, I did something wrong. Okay, and then you are getting these 2 points, and then you're just creating this hexagon. So we have hexagon in octagonal geometry, we have hexagon in decagonal geometry. They are similar, but not exactly the same. Also, we may have hexagon like this. It is easy to make it because if you take a segment on the edge, construct midpoint, and if you just make another edge, construct midpoint. So if you join them with the center of octagon, and then if we draw this line, and then if we draw this line, we are getting perfectly a shape like this, a yurt that we often used in my previous classes. So this, what I was showing you here, it shows that most of the patterns are created on a symmetric polygons built on a regular polygon, decagon, octagon, and so on. Mustafa Bulut, a professor from Turkey, wrote a book on geometric patterns from Anatolia, so-called Seljuk patterns, and he made some good statistic related to these patterns. His book, this is catalog. This is only catalog, not instructions how the patterns were created, just a simple catalog. And he just wrote that 14% of patterns in Anatolia, in Seljuk tradition or Seljuk architecture, is decagonal, then 30% are hexagonal, less than 1% are heptagonal patterns, 31.6 patterns are octagonal, and so on. The number of patterns with edges built on a polygon with more than 12 edges is just 2.32. And certainly you will not find there any pattern that was then done in tetradecagonal geometry. So you see that tetradecagonal patterns are not easy to find. You can find them a few. They are distributed in a few places all over the Middle East, but not really many. You may think why we don't have them more. You see, the situation is similar to the patterns in decagonal geometry. There are hundreds of decagonal patterns. And decagonal patterns and 10 means just 10 and 5. 10 divided by 2 is 5, and you have two prime numbers dividing 10. 2 and 5. In tetradecagonal, it means in 14, we have the same situation. We have 7 and 2. And 7 is prime, and 5 was prime. So we may expect that we may have a lot of tetradecagonal patterns because of the similarity. The fact is that tetradecagonal geometry is more difficult than decagonal or octagonal geometry. So it is much more difficult to handle. And at the time when these patterns were created, it means 13th, 12th, or 14th century, they didn't have tools to deal with 7 and 14 edges polygons. So it was difficult for them. There was so-called Neusis construction, but not many people knew how to use it, and not many people were able to use it. So this is one of the reasons. Practically two. I said polygons in tetradecagonal geometry are more difficult to deal with them, and they didn't have much tools to deal with them. In our times, we have much better situation because we have computers, so creating a regular tetradecagon, it is quite easy. So let's look at this and let's see what we can do, how we can do. Okay, but just remember, in tetradecagonal geometry, we cannot use traditional constructions with compass and ruler. So whatever you will do, you will be not able to do things the same way like it was for other patterns. Now let's make some calculations. Okay, calculate. First, how many grades we have around a point? This is 360. If I divide this by 14, I get a number like this. Okay, so this means if I divide my tetradecagon in such a way, this angle here it is 25.714 and so on. So now the question is, how much are these angles? There's also a simple thing. So we take 180 minus this angle, okay? And if you like, you can take all this and divide by 2. This way we'll get just this angle, okay? And this angle is 70.7 and things like this. Now, let's make 2 vertical lines, perpendicular lines, and now rotate. Double click means rotation. Take this thing and transform, rotate 90 degrees minus this. I cannot use this, so I can put 7, 1, 4, 2, 8, 6. This is quite good approximation, so I can live with this. Now the same I do here, transform, rotate, but rotate the other way, so put the minus here, okay, and this is what I wanted. I wanted to get this point. Now display height, okay, put these edges here, okay, and we got a polygon, a long triangle for the regular tetradecagon. It looks similar to the long triangle for decagon and so on, so we are quite okay with this. Now, if you want to make regular tetradecagon out of this, just double click on this edge and make transform, reflect, okay, then double click on this edge, yes, and then transform, reflect, and then what we do, again transform, reflect, and now what we do, we'll just select something and transform, reflect. Okay, we could do it other way, but okay, just remove it, and now just like this, and just transform here, reflect, and this is what we got. This is regular tetradecagon, and you can calculate everything what is related with this. But now I wish to just briefly concentrate on its edges, okay? So construct midpoints, and now I will just try to draw things like this. Display line style, okay, the color is black, and I can connect these 2 taste points and then these points and these points, and I also can connect these points, okay. This is what I am having here. It is just a symmetry line, and I really don't need it, okay, but this is what we are getting. Now you can just have the points here. You can calculate that all these angles are the same, but just label them in some way. Label points, let's say starting from O, okay. No, but I don't wish this way, so let's do it this way. Okay, let's start selecting, okay, display, now label points. Okay, I'm happy with this, okay, and I get a lot of numbers. And now let's label this point. Okay, label this point. I will call it O. So everything will be similar to what we did. Now, in the same way, we can label these points, so it will be practically the same. Okay, and now you can just try to calculate things like this. Okay, if you calculate the ratio, okay, or angles, okay, angles first, measure this angle, no, okay, A, O, C, measure this angle. You see, this is our smallest angle that you can have in tetradecagonal geometry. Now, let's look at this angle, measure this angle. It is 25. This is what we got. But then, if I take this angle, measure this angle, I'm getting 38. And 38, this is 3 times 12, or 857. Okay, and then A, O, okay, E, measure this angle. Okay, you see what I'm getting. This is what I'm getting. These are multiplications of the smallest number, 12.857, by 2, 3, 4, 5, and so on. So we have these lines, okay, and we can use these lines to create patterns in tetradecagonal geometry, explicitly rosettes. So we know what kind of angles we will be using. We'll be using the angles that you have here. We count them as angles between the base and the line, the section line that is going to the point. This is first time. You can create custom tools in Sketchpad or in GeoGebra just to have all these section lines ready. And then we can go to the next point. My next point are contours. Like in decagonal geometry, if I take a segment, construct two perpendicular lines. So in decagonal geometry, yes, I'm talking about decagonal. Okay, so what we do in decagonal geometry, we get this point, we take this segment, and we ask to rotate how much? 90 degrees divided by 5. I'm talking about decagonal geometry. And then transform, rotate again, transform, rotate again, and transform, rotate again, and that's all. So this was in decagonal geometry, and we had these points. Okay, and one here. Okay, so let's select these points, select this line, construct perpendicular lines, and then we create a contours like this. Okay, so this is the contour that you have in decagonal geometry, one of many. Then you have another contour like this in decagonal geometry, okay, one of many. The same way, exactly the same way we create our contours. Here we had 1, 2, 3, 4 contours. Here we have more. We have 1, then so let's go 2, further, then is 3, and so on and so on. We were talking about angles in a regular tetradecagon. Now we have to just look in how we can use these geometry. We will have for more contours. Here I just made a summary of the angles that we have, and I calculated all these 90 degrees by 7 multiplied by 2, 3, 4, and so on. I got these numbers, and if you compare left side, the numbers that are here, these are precisely the same numbers. So these would be the numbers that we can use for producing stars and rosettes in tetradecagonal geometry. So let me to start with the beginning. This first angle is just like this. I made it explicitly here because I wanted to show you that this is the smallest number. This point, it is just this point here on the edge. Okay, and how we can use this angle to produce our first tetradecagonal rosette. Look, that is the triangle that we created first. And this is the line that is the first, following the first angle. Now, if I make a bisector, I can just do it quickly. Okay, so if I do this, okay, I construct midpoint. Okay, I don't care about these numbers. And now angle 1, okay, if I take, it is my first angle, okay, I may need also the line that is the symmetry line. And now what I do, I select the top point, the corner point, and the midpoint, and I construct here angle bisector. The angle bisector, double click on it, and we treat this as a mirror. So now we take this segment, this line, transform, reflect. You see what we got? We got such a nice shape. And then again, now we use the edge, transform, reflect, and we got fine. Now what we can do, we can just take these lines, transform, reflect, okay, and by following them, we can produce a line style, okay, just medium and make it black. Okay, so this is what we do, and then just following these lines, we got so this way we got the first petal. It looks like this, exactly the same. And now we take a regular tetradecagon. We will fill it, each triangle, with a pattern like this. In Sketchpad or GeoGebra, you can always make a tool. And I made them these tool. So my petal 1, it is like this. I didn't put here the vertices, okay. There is no vertex and no vertex because when I put them side by side, this vertex and this vertex will add to the next one and so on. So I will still get these points. So our first rosette in tetradecagonal geometry, these edges are parallel and these edges are the same length. Okay, and also you can consider what will be the ratio of this. So the ratio will be bigger than in decagonal geometry. In decagonal geometry, ratio of this segment and this segment is a golden number. So in tetradecagonal number, geometry. This is a specific number that we can call a golden number. And in exactly the same way, we can produce other rosettes, other types of rosettes. So that is another rosette. It is not so nice like the previous one, but the rosette that was on the picture that I was presenting to you was exactly this one. You can also skip in this rosette these two parts and you will get a thing like this. And if you notice this, this is a trapezium with three edges exactly the same length. So this is fine. If you don't like having this rosette, if you don't like these shapes, you can always turn to the first rosette by doing a thing like this. Take this point. This is the point where the line is going, and make a triangle like this and create a rosette of the first type. So you will get a rosette like this one, and it is fine. Okay, but this rosette will be pushed inside of the regular tetradecagon. Then another angle, a larger angle, this is 3 times the smallest angle, and you're getting a shape like this. It's not so nice like the two previous ones, but you can live with this and you can get a rosette of this type. If you don't like it, you can push it up, okay? So you just take this, not this point, okay? You see just this line, okay? And then in this point, what you do, construct perpendicular line like this, okay? And then by doing transform reflect, okay, you get a triangle. So you can wipe out all this, and then in this triangle, this is our yellow triangle, okay, and in this triangle you can create a rosette petal like this one that you have here. This is the type B, and this one we call the rosette type C. And then you can also do this way, okay? You can just take your rosette here, and okay, you will get the rosette like this one. And then you can take even bigger angle, and this is quite nice angle, because in this angle what you can notice, okay, so if you draw the circles, you will get these 2 points, okay? So you don't need to remember what kind of angle you were using, but you're getting this point, you're joining them with the midpoint, and then doing a reflection, you get this point. So we didn't get rosette, we got a star, nice star with a huge interior. You can do with this interior what you want. You can insert a rosette inside, no problem with this, okay, or a rosette like this one, okay. It is slightly bigger than the previous one, okay, and this will be still rosette B type 2, okay. And let's go to the next angle. In the next angle, what we have huge segments like these, and of course, again, if you look at this number 2.8019, it means the ratio between this segment and the short segment is about this, okay. So this is what we got in the previous in the beginning. Now if we look at the stars and rosettes that we created, we can make a kind of summary. So for the angle one, this was first rosette or element of the first rosette. For the angle 2, we had rosette angle, a rosette element like this, or we could move up and then we get the same rosette like this one but pushed inside. Then angle 3, this was the angle 3, 8, this is 3 times this one, and then we are getting a rosette petal like this. For angle 4, we have 3 solutions. One solution, just a pure star, another solution with a rosette that is pushed inside. In fact, what I should do, I should push, okay, this is the real order, okay, so here the rosette is just touching the star element, here the rosette is just built above this hexagon. Then for the angle 5 we got a thing like this. It is quite nice star, in fact a bit boring if you talk about elements, but sometimes you may try to use it. And then you're getting a star like this one, okay, and this is the star, okay, that's the point, and then this is the star with very long petal. So that is the summary of petal and star elements. In the paper published in the proceedings, you have more drawings and, let's say, more detailed information. Now let's move to the part 3, okay, and we start with examples. Examples are important because examples are showing what we can do. Okay, so for example here, what I did here is like this. I took 2 tangent tetradecagonals. 2 tangent tetradecagonals. That is essential. So this is the first and the simplest example that you can get. Okay, in more complex examples, the space between these 2 tetradecagonals, there will be no tangent and there will be some polygons around. Now, what I did, I took 2 tetradecagonals, I connected their centers with a segment, I found a midpoint, that is fine. Okay, and then I took a third point. Okay, but what is the third point? The third point is on the circle with the center in the midpoint, and the radius is up to A or B. It is up to you. So the circle is passing through AB. Now, from mathematics, high school mathematics, you know that if you take these 2 points, draw a segment, and then if you take these 2 points, between them there will be always a right angle. This is just school geometry, high school or sometimes primary school, depending on your education system. Now, let's ask question, when we can create a proper pattern. Okay, so look what we gain in getting. Normally, when we have a situation like this, we prefer to have one of these edges passing through the point, okay, the radius of the regular polygon, and the other one passing through the midpoint of the edge of the another regular polygon. This is the same for decagons, octagons, and so on. The same is for tetradecagons. So you have one situation like this, and you can be quite happy with this. And you can also go this way, okay, just to have this segment covering the midpoint, and we are getting a shape like this. In fact, these are two identical rectangles. Only one of them is the rotated version of the another one. So let's look at this. How it was created. It was created this way, that we draw a segment, we draw two vertical lines, okay, and then we build lines this way, okay. Okay, and of course here, and of course I don't have points, so I can just cheat a bit. Okay, so what you see here, you see a perfect construction how to make two tangent tetradecagons and how to build the contour and how to make a tessellation. So by dividing this angle in 7 parts, we are taking 3 of them, okay, and this is the red line, okay. If you do the same in the other way, you will get, okay, let me to show you. If you do this the same way, you will get these 2 points, okay. You can make it bigger and see what you're getting. Now you can go along these circles, and then you can yes, okay, and then you can create a tessellation. First around the tetradecagon, and then you have to just deal with this space. It can be dealt in 2 ways. One way, which I normally prefer, this is the one here, and another one that is not my favorite, because here you getting long edges and short edges, and that's fine. Here this edge seems to be equal this one, but it is not. The one here is shorter than this one. You can just, okay, you see that this one, this horizontal edge is longer. But anyway, let's have it here drawn properly. So we may get 2 hexagons like this, okay, and then 2 kites like this. This is a very nice construction, and you can do a lot with this. Or you can have the 2 hexagons and triangles like this, and here is the construction of half of this hexagon, okay. This is the construction that you can follow. It is not quite difficult. You just do this, what you have here. Start with this line, and then draw these 2 lines. Okay, you get these 2 points. So you draw the horizontal line, and then you draw this line just to get this point, and then you go this line just to get this point. So we constructed this hexagon in a regular tetradecagon. It's simple construction, but it's not the happiest solution. And now, if you have this, you can fill this rosette with what we did before. This is just the way how we do everything, step by step, top down. Okay, and now, so you have the petals already. This is the petal A, and then you have to just fill the other polygons. So you can fill it in 2 ways. One, by going along this line and getting it here. Then another one, which is just this line. Okay, I have to get it. Okay, this is this line, and it is reflected, okay? Angle here and angle here is the same. So we get this, and for the half of the hexagon, we have a solution like this. It's not very nice solution, so we may also use a solution of this way. You just draw a circle, that's your circle, and the circle is passing through this point. Just take this point, draw vertical line, and you get this shape. It is nice work, but at least you can find a pattern that is using. But both of these solutions are precisely correct. So we getting this, okay, and then we making a bigger pattern. So I am just showing you here what you can get with this, okay, with this combination, okay. So this is what you're getting. So that is a regular heptagon, and that is a nice shape, a very good, very nice looking, okay. And then here is a larger pattern built out of this what I did. So this is the pattern which is from Cairo. This is one of the very few tetradecagonal patterns existing in real place. The only difference is that they didn't use this solution, but they used this solution, okay? So the pattern from Vakala Al-Guri is like this one, but with these hammers like this. Okay, let's go quickly further. If you take the same tessellation, but if you take a rosette type B, this is our rosette, okay? So this is what we did. Okay, so this is type B, and we are just producing a template for the pattern. I don't like this part, but this is just, again, closing the regular heptagon, and the pattern is quite nice. Simply, we can use it, but I didn't see even a single pattern in real life made this way. But it looks nice, okay? If you make it in color, you will be absolutely fine with this. Now, the third angle. For the third angle, this polygon that you have here, okay, this is the hexagon that I was telling you I don't like it, but here is very useful because you can make a pattern filling it. That's another part, okay. I can just draw. This is not a proper drawing. Okay, so this is how it looks. Okay, so, and then you can just see that you are getting this part here. So you will be fine with this pattern. If you don't like the large empty space, you can always fill it with some extra lines like this, okay, and you can get something that will be more interesting. Okay, let's go further. You can also, instead of the star, put a rosette here. It will be not looking good because you're getting big spaces and small spaces combined together. And then you can get a pattern like this. This is still the same angle. So we had the angles like this. Okay, this is the summary of all angles that we use for these constructions. You can also play with different ways of dealing with this, so that is fine. Okay, and let me to finish this thing. So I thank you for attending this lecture, if you attended it. I thank you also for watching this presentation, if you see it online, and I hope you like it.